Good, good evening, one and all.
Okay.
Sir, shall we start the session, sir?
Madam, Priyanka madam,
Yeah.
చెప్పండి.
Yeah. Good evening. Good evening,
Okay,
sir.
sir.
Yeah, I welcome Alex for this session. I request Priyanka madam to give brief introduction about. Yeah.
Okay.
Yeah. Priyanka madam.
So good evening, very good evening to one and all. I, G. Lakshmi Priyanka, Saint Matt. Sir, please, sir.
Yeah. Go ahead.
Yes, sir. Engineering College, Assistant Professor. Okay, sir. Okay. Sorry for the interruption. So very good evening to one and all. I, J. Lakshmi Priyanka, Assistant Professor, St. Martin's Engineering College. Welcome all of you to our international online workshop on IoT and cloud computing techniques and for data analysis with modern AI tools, 16th and 18th August 2020. So today I would like to introduce our guest of honor, Dr. Alex Noel Joseph Raj, sir. Sir, I would like to introduce about his profile. Sir has completed his BE from Madras University in 2001 and Sir has completed his MTech from Anna University in 2005 and Sir has completed his PhD from University of Warwick in 2009. Sir has worked as a design engineer in Valeport Limited, Totens, UK and Sir has worked as a professor in Department of Embedded Technology DIT University, Vallur, India, and Sir has from since 2000, March 2017, Sir has been working with Chantal University, China, in Department of Electronics Engineering. And Sir's area of interest include signal processing, image processing, and his areas also include radar processing. Sir has published more than 58 publications, many international journals, and with 132 citations. So today, with a great honor, I will request Dr. Alex sir to take over the session. Sir, Alex sir.
Hello. Are you able to hear me?
Yeah. Yes, sir. Please go on, sir.
Sorry, I'm unable to hear you.
Yes, sir. You are audible, sir.
So I'm audible, right? So, okay. So should I start my presentation?
Yes, sir.
Okay, fine, great. Can you give me allow me to share the screen, please?
Please share your screen, sir.
Could I start?
Yes, sir. Yes, sir.
Yes, sir.
So very good evening to all from St. Martin's College. So I'm Dr. Alex Noel Joseph. So I'm a professor at the Chantal University in China. So today I'll be speaking about text detection in natural scene images. That would be my topic of today's presentation. So it's just about me. So I have a PhD from the University of Warwick, top 100 universities in the world, and I specialize in computer vision with FPGA implementations. So I work on biometrics, shape reconstruction, text detection, UAVs, ultrasounds. So many of those things I work on. And I also work on real-time implementations on FPGA as well. These are some things I do for my research with my PhD students, as well as my postdocs, as well as my master students. Okay. So if you want to know where Chantal University is, I've just drawn this over here. We just have some idea about it. So this is China, and Chantal University comes along the east coast of China. So this is, you got your Japan over here and your Hong Kong over here. So Chantal University is about 1 hour by flight from Hong Kong. It's a very small university, but it's a full-fledged university which has got medical schools, business schools, English language center, and many things. Yeah. So we also have some good research facilities and many key laboratories as well. And I belong to one of the key laboratories which work on artificial intelligence and robotics as well. Yeah. Okay. So today's presentation, what I'm going to do is there are 3 different things in this. So I will start with a brief intro about neural networks. So many of you probably know about this. So I'll be just giving you a brief outline about it. Let us say outline about this neural network. Then I'll be going into a deeper inference about feature description. So I have been working on in this feature descriptor called Zenlike Moments for quite some time, maybe like 6 years I've been working on this, and along with my PhD students. So I published quite a lot of papers on this particular area. So, and recently we have done a work on application of these Zenlike Moments in detection and localization of bilingual text. So basically it's English and Chinese language. So we have used Zenlike Moments to find out text in images, if you want to give an outline about it. So the presentation would start with a simple neural network, feature description, how to use Zenlike Moments, and finally, how we used it use Zenlike Moments for detection and localization of text in natural images. So this will be the flow of my presentation. Okay. So all of you must have seen this this diagram at some point of time. So you call this as the neural network. So you have an input layer. So you call this as some kind of a neurons. So let us say this has got neurons, and you give some inputs to these. Okay. And you got another layer which is called the hidden layer. And finally, you also have another layer which is called the output layer. And in between, you have some connections. So it connects some kind of neurons from first layer to second layer, some kind of a connections you can have this. And you call this as a fully connected. If you connect each of these neurons, the first layer to the next layer, each of the connections goes to one among the hidden layer, you call it as a fully connected network. Okay. So what happens is you give some inputs, and you have a error between desired minus actual. So you get some error here, and you propagate this error backwards. So you call this as the back propagation network, okay, BPN. And based on this back propagation network, what happens? The network generalizes, and it comes to a position or comes to a state where you call this the network has been trained. Okay, so you've got some images, you give it to the input, the input, the network trains and trains and trains, based on the error. So once the error comes to some kind of criteria, you say the network has been trained. Okay. So probably you know this, and let us go into some kind of inference about this layers. The first layer, you call it as an input layer. So what happens in the input layer, you accept some kind of features. So you accept features and feature labels. The next layer, which is called the output layer, which tells you the score. Okay. So the input layer accepts the features along with the class labels. Let us call it as a supervised learning. So let us call it as a supervised learning. So you got a feature vector and a label. So you give it to the input layer. The layer trains and trains and trains. And it gives you a score at the output layer, which is basically the decision by the network. Similarly, you also have a layer called the hidden layer, which computes some kind of information. And all these things, you call this the connections between the layers are called as the weights. And you have some biases as well. All those things get updated as you back propagate the error. And once you back propagate the error, what happens is you tend to say the network has been trained. Fine. So here is an example of how the network is getting trained here. Let me show you that. Yeah, let us go into this a bit. Yeah. So can you see it? So as you run through this neural network, what happens is each of these layers come to some kind of saturation. So you can see here, after some training, the first layer comes to some kind of saturation. And later, the second layer comes to some saturation, the third layer comes to saturation. And finally, as the network trains and trains and trains, it comes to a generalization where you say the network has been trained. So you can see this. This video is taken from the YouTube, and you can have a look at this, how the network is getting trained and how it is getting generalized on this. Okay. Now, let us go into the next bit of it, of the neural network, where you can see this part here. I explained you about this part, where I told you this is the input layer, the hidden layer, and the output layer, and you have some weights here. Okay. And suppose, let us take a example here. You want to identify whether this input is a car or not a car by this network. Okay. So what you do is you can either give this whole image as an input to the neural network, or there's somebody sitting in front of the neural network. Basically, somebody is sitting here. So what is his job is to extract the features. Features means some important aspects of the image. Let us call it like this. So some person has to sit down and he has to extract some important features or the important aspects of this image and put it into the first layer of the neural network. For example, if you want to differentiate between a car and a human being, so or a non-car, what you can do is you can say the car has got 4 wheels, the winds, so you can say 4 wheels. This could be one feature. Maybe the shape could be a feature. Maybe it has got a kind of a oval shape. Shape could be one of the features. Then you also have windows. So these are some of the features which you can give it to the network, and then you can allow the network to train and train and train so that it generalizes. And then what happens? It can able to differentiate any image as a car or not a car. So this process of extracting some kind of information from the input image, this is called as feature extraction process. And if you look closely, the literature, if you look into the literature, there are so many ways by which features can be extracted. And over the years, many have developed their own features as well. Let me click on this a bit more clearly. Okay. So you got the simplest Fourier descriptors where your Fourier transforms can be used as descriptors. Then you got the HOG, the histogram of oriented gradients, shift patterns, local binary patterns, local directivity patterns. Your DCTs could be also used as features, wavelets, invariant moments, bag of words. So in the literature, you find loads of information about features. And you can use any of these features in order to give it to the input of the neural network. Okay. Now here comes the catch. So though the features are effective in representing and describing the images, the accuracy of the system depends on how well you extract these features. That's very important. Suppose in our example, you got the car and the non-car, car, non-car. So instead of saying 4 wheels, you're saying 2 wheels. So what happens here? You're not extracting the correct information, the correct features are not extracted. So what happens? A bicycle could be classified as a car. So the bicycle will be classified as a car if you don't extract the features properly. So in the feature representation and description, it's the accuracy of the system depends on how well you obtain the features. Poor features leads to poor accuracy. That's more, you have to keep it in mind. If you're not able to extract the features very well, automatically the accuracy of the system goes down. Okay. Coming back to it, let us take an example of how you can describe a feature. So this is a simple, I can call it probably everybody knows this, it's an elephant. Suppose I ask you to describe this elephant. So what you can start off thinking about from this image, what are things you can say? So the first thing you can say about is in terms of color. So you can say the elephant is like, black or gray in color. You can say that aspect. That's one thing. Yeah, you can say in terms of color, the elephant has got a peculiar color. Now this represents some kind of texture of the elephant. Okay, some kind of texture of the elephant. And you can also go deeper into one more step. You can start to say about how the elephant looks like. For example, it says gigantic, which means the height and the width. You can call it as the aspect ratio. Okay, so it has got a huge aspect ratio. You can just conclude like that. Then you can also say something about how it looks like in terms of the legs. Say it says 4 legs. Then you can say it has got large ears, tusk, and of course a trunk. So these are the few distinct things the elephant has got when it compares with other animals or other mammals. So what you have done here is you are trying to extract as much information as possible about the object. So you're trying to extract, say, you can also say that, the size, the height, and all the information is extracted. And what I'm doing by this way is, so while extracting is, you're trying to describe the object as most closely as possible. And this aspect is called as the feature description. And when you try to describe the feature, one of the most important feature, if you look closely, is basically the shape. Okay? So this is one of the most important feature. Okay. This is the most important feature of anything. So you got texture, you got color. But of all of these, if you look closely, shape is the one which you would be able to recognize. For example, you can recognize an apple from a banana, not just by the color, but you can recognize by the shape. Maybe a car from a bicycle, and different types of cars as well. You can recognize by the shape. So, as for the from the computer vision point of view, shape is one of the most distinct and vital feature which you can extract it from any image, and you can fit it into a neural network to train it, and so that it can recognize that particular object. Okay. So the research, what I'm going to speak is, or what I'm going to tell you, the next, the slide is, how can we extract shape? using this particular moment called the Zenlike moments. So how can we use, how shape can be extracted using Zenlike moments? So you can also say this Zenlike moments a useful shape descriptor. Okay, quickly to just summarize whatever we studied, we went through it. So we let me go back again. Okay, fine. Yeah, coming back into this. Yeah, now I'm going to tell you about few things about Zenlike moments. What happens here? So Zenlike moments are a class of 2D polynomials. So you can say them as they belong to a class of two-dimensional polynomials. You can say 2D polynomials. So two-dimensional polynomials, basically they're used for images. So it was, I'm unable to see my screen because of this thing that pops up. Let me remove this. Okay. Fine, moved up. Okay. So Zenlike moments, as you call it, or the Zenlike polynomials, are a set of two-dimensional polynomials. It was, one second, give me a second. Yeah. So they are a class of 2D polynomials which were found by a person named Fritz Zenlike. Okay, so he was a physicist, and he won the Nobel Prize for physics while he invented the phase contrast microscope. So in 1953, he invented this phase contrast microscope, and he also theoretically proved the Zenlike moments. So initially, Zenlike moments didn't find that much of usage. But suddenly, when they start getting a big usage in the optical manufacturing industry. Okay. So why were they used? So they were used to find out errors between an ideal spherical lens and that which was manufactured, So they had an ideal spherical lens, and they were able to compare it with a manufactured one. In fact, like a quality inspection. They're using Zenlike moments for quality inspection. And they were able to find out how the manufactured one is, is better, or is it close to the actual ideal one. So they were using Zenlike moments to do that. And the second thing about Zenlike moments is they are orthogonal. So you have to understand this word. It's orthogonal. The word orthogonal means, suppose I have two features A and B. These two features are unique. So you got unique features in them. So these unique features are really important. Okay. So what happens is with the unique features means every feature the Zenlike moment gives you adds some information, which means suppose you have 50, features. All these features add some unique information which help you to represent the image far better. And you can also say that with Zenlike moments, there is no redundancy of information, or there is no overlap of information when you use Zenlike moments. Okay. And lately, people started using Zenlike moments as image descriptors. Suppose you want to find out an object, you are able to find out the shape of the object, you are starting to use Zenlike moments to identify the shape of the object. So let us go into some examples. So right now there was theoretical over here, and this is, I'll come back to this. Yeah. Let us go into some kind of, some practical information about the Zenlike moments here. So this is an input image, and you can see here the outputs of the Zenlike moment. So this is output 1, and this is, let us say, output, say 5 or 8 or something like that.
Excuse me, sir. Excuse me. Sir, can you hear me?
Yeah, I can hear you.
Hello.
Yeah.
Yes, I'm Dr. Anand speaking. Sir, some of the participants are saying that they are not audible. So 2 minutes, we'll reconnect that one and we'll do that one, sir. Or some of the participants. So just sorry for the interruption.
Okay.
Please, all participants, wait for 2 minutes. We'll do the connectivity issues. We'll do it and come back to you.
Shall I start from? Okay.
No, sir, as it is, as you this, and we'll come back to you, sir. Oh. 2 minutes, all of you. Please make a patient. Within 2 minutes, we'll be back about.
Hello. Yeah, what happened? Hold. Okay, can I start?
Yes, sir, you can start,
Yeah,
sir.
sorry. Yeah. So basically, we were somewhere. fine. It's been shared. Okay, great. Fine. I have to reposition this a bit. Okay, great. Okay, so we were here in this slide. So I was explaining about the Zenlike moments. So what are the things that have been, so I told you. Okay, so I told you Zenlike moments were developed by this physicist named Fritz Zenlike. So who won the Nobel Prize for the phase electron microscopy. And basically these were used for finding out defects in optical industry. So they were able to find out the difference between an ideal piece and those that has been produced, manufactured. So basically it was like a quality inspection program. They were doing it. And the good thing about Zenlike moments is they were called as orthogonal. I also explained you, which means two features that come out are unique. So what are the features you get across are unique features, and which means there is no redundancy, and every unique feature that you get is adds some information towards the feature description. So let us go into the next slide. This is about the mathematics behind Zenlike moments. Okay, so if you have an image, so let us say this is an image. What you do is you just project the image onto the Zenlike polynomial. So this is the Zenlike polynomial. This is basically a two-dimensional polynomial. So I think many of you know about the Fourier transform. So what you do is in Fourier transform, you take x of n and you project in terms of e power I theta, where e power I theta is nothing but cos theta plus I sin theta. So you take an image, a signal, and you project it onto this basis function. This is the one dimension. And similarly, for the Zenlike moments, what you do is you take your image and you project it onto a two-dimensional polynomial. So this is the two-dimensional polynomial here. And you can vary this polynomial, basically. You can vary this polynomial by varying the order n and the repetition factor m. So as you vary m and n, so as you change m and n, what happens is you try to get different moments, and all these moments add some information. So let us go to this slide, the next slide here. So I was about to show you this. So now this is an input image. So let us call this as f of x, the input image. And I am projecting it onto the Zenlike polynomial. Let us solve v of m comma n comma m. And as you change the order of m and n, you just go down this way. So this is the order. You've got a order being increased along this direction. So you increase the order. So what happens is, if you just look closely, the first order, what you can do is you can just get some information, very less information on this. But as you increase the order, you can see here, when I increase it to at this position, say, let us see, this has got a big order here. You can see, you can get more detailed information. So here you get some kind of a global information, but whereas here you get detailed information, which means as you increase the order of the Zenlike polynomial, what happens is you get more and more finer details, and all these finer details add some information towards classification or towards the shape of the particular object. So this is a very good, so you can increase the order of the polynomial and you can get more and more information, and all these information are unique, which means all this information add some kind of detail to this shape, and these information would be readily useful for classification part. So now, after working on with Zenlike Moments for some time, we can get into these few information. One is Zenlike Moments provides shape information. As I told you, this is a shape descriptor, a 2D polynomial, which is basically describes the shape. And you can use the magnitude of the Zenlike moment to describe or represent an object. The second thing. And the third thing is, Zenlike moments are invariant to rotation. What happens is, something A and a rotated A both have, the same Zenlike moment. So you can able to define the rotation as well. You should be able to do it. So I can extract this Zenlike moment and this Zenlike moment, and I can say that the rotated A also belongs to the actual A. The Zenlike moments are unique for these. They are orthogonal, which I mean they have unique information with no redundancy, and they got scale invariance, translation invariance, all these things are available. And finally, there's one important thing about this. The lower order moment capture global information. This is more important. So you can see here the lower order moment captures global information, whereas the higher order moments, if you start increasing the order of the moments, you get more and more detailed information. That's more important here. So things like, you get the shape out of Zenlike moments. The shapes are invariant. So if the shape is rotated, you can actually identify using Zenlike moments. They're orthogonal. I told you what it means by this, which means every Zenlike moment that comes out, it's redundant. It is non-redundant, which means it adds some information. It is scale and translation invariance. And finally, lower order moments capture global information. And as you increase the order of the Zenlike moments, you get more and more finer details of the image. So this is something, we went through it and we analyzed it for quite some, times. And let me quickly recap what are the things I was teaching now. Maybe I can just quickly go through it. What are the things we discussed now before we proceed into this? Okay. So the first, when I started off, I spoke about neural networks. So I spoke about this. Then I spoke about feature description. And I told you, shape is a vital feature descriptor. It's one of the vital and one of the most important feature descriptors. Then I told you about Zenlike moments as one of the shape descriptors. And I also given you information about the Zenlike moments. Say, for example, they are orthogonal. They are orthogonal, one thing. They are 2D, two-dimensional. The second thing, the last thing I told you was, you get global as well as detailed information from the Zenlike moments. So these are some things which I actually told you over the past few slides. Now coming back to the next one, how can we use Zenlike moments? Okay. Fine. So this is the last step of my presentation. So how can we use the Zenlike moments to do text detection and localization in scene images? Fine. So this is what you will be seeing at the end of the slides. Another 10 or 15 slides, you should be able to see these kind of outputs. So this is called as text detection in natural scene images. So if you want to do some kind of AI project and you want to have more data sets and other things, one of the best areas to concentrate is on text detection using natural images. The reason is there are loads of images available on the internet. You can also take those images as well from your simple camera phones, and you can develop your own algorithms. All you need to do is find out where the text is present in the image. That's all it is. So this research has been there for like 15 to 20 years, and many researchers, especially in the Southeast of Asia, they have done algorithms based on this. And I also tried one of those algorithms, which is basically using invariant moments, what I call it Zenlike moments, along with this statistical filters. So these two things I will use to detect those texts. So the second set of my topic, I will speak about the need for text detection algorithms. So why we need this text detection algorithms? Some of the existing techniques. So very briefly, we'll go through it. I'll speak about our approach, results, limitations, and I'll also give you some scope about the future direction. So what are the ways you can go through the research? So this will be like another 15 slides. You can just go through all these things. Same. So need for text detection in scene images. The word scene is basically, you can refer it as the natural scene images. So natural scene images is basically any images you take it from your photo, from a mobile phone or something like that. Some examples I have shown here. So this is 1, 2, 3. Some natural scene images which have got text in them. Okay. And you know that all these internets are flooded with so much of information, images, and all these images contain some kind of high-level information. If you are able to decipher or able to extract that information from these images, then you should be able to do quite a lot of information like object recognition, image retrieval, multilingual translation, so and forth of so much of different applications you can use once you are able to extract information from these images. It is not that easy to work on this natural images. This one you can call it as text detection in documents, and this is some examples of natural scenes, and this is with documents. So you can see here, documents, you got a very nice white background on top of and the text is like a black contrast. You can see that. And you got a similar same fonts going all the way. You got spaces between words. The character are all of same size and all that stuff. And other thing is the orientation as well. All of them are equally oriented along the horizontal direction. So on comparison, if you look this way, you can see the challenge here. The first one looks quite promising. You got a black text on a white background. That's quite well. But the text has got an angle. You can see here, there's an angle between these things. The second image, it's okay, but you've got additional background information here, which looks like text as well. Here, the text background and the text as well as the background almost look the same. Here you've got some shadows here. And in this one, you don't have any text, say about 70% or 70 to 80% of the image, you don't have any text. And this is present only at this point, So this is the problems. So there's a huge challenge when you want to work on text detection using natural scenes. And I will list out some of the problems here. You can just list down here. You have different things. One is color, font, scale, orientation. All these involved. All these problems come under if you want to work on natural scene images. Then you have inferences, interference from distortions, low resolution, occlusion, all these things come when you want to take, an image. When you just take an image, from a camera, you get all these problems. And you also have some components which look like text. That's also there. Some of the components like fence and bricks, they also look like text, which becomes a problem while detecting it. And since people have been using this this kind of text detection applications for quite some time, and many people are developing algorithms, Microsoft released a data set. This is a data set that was Microsoft released it. So they released it in 2012, along with a university called Hangzhou University in China. They released this data set, and it's a publicly available data set. And you can have a look at this. Here, you've been asked to spot the text. So it's, I think many people failed it, because you got a huge background here. Can somebody tell me where the text is? If you can. If you can just say where the text is. If you want to have a look at that, I'll just go to the next slide. The text is, at this point, the topmost part, you can see the text here. Can you move this somewhere? Yeah, the text is somewhere at this particular point here. And we have been asked to identify this. This is the gold standard. The green one is basically the gold standard, which means the humans say there is a text there. And you expect the algorithm to detect this text. The problem is this 99% of the image has got no text. And text is at only that particular small region, which we need to identify. So most of the algorithms fail in this, and you have been asked to identify an algorithm which can do this process. So there are so many techniques in literatures where people are using this, and I'll just go through quickly some of these. One you call is as texture based. Texture based is text always has got some kind of a color or some kind of a texture. So when you write, say for example, here I say texture, the texture is of it's got some kind of color with respect to the background. So you can use some simple image processing techniques to identify where the text is. Then you also have techniques like, connected components, where you can see edges can give you some information about the text. And then there is something which is quite recently people starting to use, which is called the sliding window technique. Okay, this is called the sliding window technique here. People used to detect text lines and regions. So they run through like a convolution thing. They run a sliding window on the images, and whenever they find text lines, they keep a note of them. Then they extract the features, and then they train it to a neural network, which gives them where the text is. So that's called, sliding window technique here. And you also have a combination of these four techniques, which is called the hybrid techniques as well. So you can combine any of these, and you can have an hybrid technique here. Okay. This is an example of a texture-based technique here. You can see the text having some kind of a same format and color as, which is different from the background. You can use the GLCM, which is called the gray level co-occurrence matrix, to do this. Then you can have edges, stoke with transform. So this is called the stoke with transform, which tells you as you move from the background to the foreground, there is a change in intensity level, and this intensity level is seen as an edge. You can use that information to detect the text. And this is what I was speaking to you about the sliding window technique. What happens is you move this window. This window has got 1, 2, 3, 4 subdivisions. So you move this window along this image, and as you see here, as it comes in contact with the text, what happens? You find the similarity between these two red regions, and you find the dissimilarity between the red and the green regions. So if it comes exactly in the text region, the red regions will show high similarity. The red and the green regions will show poor similarity. So basically, by using this idea, they were able to identify different text regions here or text lines here. And once you identify text lines, you should be able to identify where the text is. So of course, you have to run through different window sizes. Say, yes, run through 3 different window sizes here. And basically, then you took, the average of all those things, and you was able to find out where the text was. So problems associated with these techniques is, one thing, if you have a very poor contrast, the textures, descriptors will fail. Objects which have got, scene which looks like objects which are, for example, fence, they look like text, they have some kind of regularity. In those cases, edge descriptors will fail. And the sliding window technique, I told you, it's very, very slow. It moves slowly on the image. And as it moves and moves and moves, it becomes computationally very intensive. So it has got its own problems. So keeping these things in our mind, we developed our own algorithm. Okay. Coming back to our algorithm, so we had 3 different things in our mind. One is, can we reduce the area? So if you look here, the background takes about 95% or 99%, whereas the text is only visible at this point. So if you are able to reduce the background, you can reduce the background, find the text regions, we can actually improve the computational speed as well. That's one thing. Then what do you call this as? You identify these text regions, you call this as text proposals here. So once you identify these text proposals, you try to extract some kind of information, the shape information. So here we do have Zenlike transforms to do this. So you try to take the text proposal, we apply Zenlike transform to that. And then we take those features and give it to a simple ANN classifier to say whether that particular region has got text or not. So what we do, 3 steps we do. One is remove the background as efficient as possible so that we have very small region to locate and search for the text. So once we call those regions as text proposals, let us call like that. So we take those text proposals. Then what we do is we extract some shape features. In this time we use Zenlike Moments to give us the shape proposals or shape features. Take the shape features, train them with the neural network, and tell whether that particular region has got text or not. This is the procedure we followed in our algorithm. So to do the reduction, well, let us get the background reduction. So we want to reduce the background. What we did is we took 2 things. One is variance and another one is entropy. So variance gives you the changes in intensity. So variance is basic. So variance is square of standard deviation. Standard deviation is basically movement of the mean, deviation from the mean. That's what standard deviation is. So you find out what are the pixels which have been deviated from the mean. Then entropy gives you the homogeneity of the region. It gives you the homogeneity of the region. So for example, text regions are all have homogeneous, patterns. So we take these 2 things, then we do a small mechanism where we find out all the pixels which are above the median. Then we do an intersection of these 2 things. And finally, we are able to narrow down the text region by eliminating the background. So this is what we did. So we took a variance filter, entropy filter. We took some pixels which are above a median value, and then we took the intersection of these to locate the probable text regions by removing the background. This was quite simple, and it was giving us some good results. For example, in this image, variance was giving us the edges, entropy was giving us the homogeneous regions. And when you take a combination of these two things, we are able to locate the text quite well. And you can also see some more images here. In fact, this one was actually removing most of the backgrounds here, and we are able to locate the text. And similarly, we were able to locate the text by removing most of the backgrounds. We were able to do that. But this was not so easy when you have this kind of an image, where the text has got less contrast with the background. This becomes a problem here. So here you can see the text has got the same color or similar color as the background. And if you just apply any kind of statistical filters, this is what has happened. You get your background as well, along with the text. So you can't actually detect the text, even though you can remove some regions here, but you can't actually detect the text, or you can actually locate the text in the background. So this is what happens when you apply statistical filters. So to deal with this kind of problems, what we did is, we went through a process called pruning. So what we did is, we took the original image, we applied this entropy and variance combination of filters, and we tried to locate the regions. So these are three different regions. So region 1, region 2, region 3. And we set across a score. And we call some regions which are higher than a certain score as abnormal regions. Say, for example, this one has got a bigger score. We call them as abnormal regions. We took these abnormal regions separately, and we had another algorithm there. This was a sub-algorithm. We had a main algorithm. Then we had a sub-algorithm, subroutine. You can call it a subroutine, which was actually a series of other things. For example, contour deduction, corner deduction, sliding window to find out the slopes. So all these things we did across on the abnormal regions to identify text with this pattern. So what we did here is, in the pruning aspect, we tried to localize the text regions in these abnormal regions after applying the statistical filters. This is what we did. So we took the abnormal regions, we applied a series of other small sub-block algorithms, and we located where the text is in those abnormal regions. So now we have probable text regions directly applied from the statistical filters, which means which are satisfying the scale constraints. This is what we did. The second one, the pruned ones. And finally, once we have all these things, we pass them to the shape descriptor. So here we have Zenlike Moments as the shape descriptor. So we passed it to that, and that was giving us the features which we can use it to train the algorithm. So in this case, I'll just quickly go into this one. Will be having the text proposals. So maybe the text regions will come here, and this is basically the polynomial, and you've got a huge formula to compute this polynomial, and you can change this order of this polynomial to get different information. So here is an example here, how we apply the Zenlike feature maps. You can see here. So this is the text, background. You can see the text shows a different pattern. The background shows the different pattern. And this is the order we used. So when you change the order, you get different information, and all this information add to this. Okay. So what happens is, once you have this kind of information, you can actually say text can be separated or text can be classified from the background. Here you can see here, we took some examples here. This is some scene images. You muted me again. Hello? Am I audible?
Yes, sir, you're audible.
I'm sorry, I something wrong. Okay, fine. So here you have a text region and a non-text region. And what we did is we took the Zenlike Moments here and we compared it. So here you can have the text region, we took the non-text region, we took the shape descriptors here, and you can see here, there's a nice difference between the non-text region and the text region. So the classifier can actually find out a separating line between the text region and the the non-text region, and the classifier can easily generalize. That's what we have done some analysis here to say that the Zenlike movements can be actually used to detect text and non-text regions. So keeping this in mind, what we did is we resized all these text proposals that we have. So we had like say 5,000 of these. We resized them, and we extracted 72 different features. Not 1, 2. We went across 72 different features, which means we got 72 unique features. Okay. As I told you, Zenlike Moments gives you unique features. So we had 72 unique features which are invariant to rotation. And we took this 72 unique features and we gave it to the input to the neural network. And we allowed the neural network to train in a supervised learning method. So I expect you to know supervised learning, because we say, so supervised learning means we have text and label. If it is a text, we say 1. If it is a non-text, we say 0. So likewise, we give it to the neural network for it to train. So this is a supervised learning. So somebody has to annotate the ground truth and they give it to the neural network to train. And we take 72 unique features to train the neural network. And this is the entire flow chart of the algorithm. So as I told you, the scene image goes into a combination of entropy variance filters, which removes the background. So you remove the background as close as possible to the text. We remove the background. So this is basically background removal. Then we identify the text proposals. We extract the text features from this. We extract the text proposal and we find a score to it. We give a score. If the score is above a criteria, we say it is abnormal. We still prune this here. Then if it is below a particular region, particular level, we call it as normal. In both cases, it goes into a shape descriptor where you take Zenlike moments to it, train the feature vector, and test it. This is what we did in this entire paper of ours. And we worked on this Chinese English language data set, which was released by the Microsoft in 2012. So last year when we did, it had an F score. So they give us benchmarks. So every year they give us a benchmark for the score. And the score was 0.65 when we started off. So we have to break this score. We have to give a better result than the score. And we call this as the F score. Okay. So we did some couple of performance analysis on this. The first thing is how well our statistical filters, are good. How well they remove the background. That was the first thing we did. So we compared with other techniques. So ours was giving us like 17 text proposals per image. So after removing the background, we were having 17 unique regions. Whereas other techniques were giving like 1,000 to 2,000 or 100 to 1,000 regions per image. So we are saving quite a lot of that, which means we have removed quite a lot of background. And if we just worked out how much we saved up, we had a saving about 72%, almost 73% saving in terms of background. That's what we did. And then we did some, the classifier performance. We call it as a classifier performance. We give the text region, we give the non-text region, and we say how this text, the algorithm, the classifier performs. For example, you expect, say, these 60 ones to be classified as text. So we had 115 regions being classified as text, and 60 regions have been misclassified as non-text. So totally, we had about 1,175 regions. Out of 1,175, this many were correctly classified, and 60 were wrongly classified. And similarly, non-text being classified as text. This is with the training accuracy. And similarly, we did the testing accuracy as well. So we got about training about 98, and for the testing, we got about 95. So obviously, this is going to be lower than the training score, which is we expected to, because these are unseen samples. So these are unseen samples, so we expect the classifier to give a lower score than the trained samples. Okay. The second thing we have to do is, we have to find out a bounding box as close as to the text. For example, the green ones, they are marked by the humans. These are being given by the Microsoft. So we need to find out how close we can detect the text to this bounding box. So this is also one of the criteria as well. So how close we can get it to the actual ground truth bounding box. And we did some analysis as well. You can see the precision and recall as well. And if you look closely, after doing it on the testing set, our method was slightly better. So we had a 0.67 was on 2019. We had a score where the 0.65 was the other score we had as well. This was from the other paper. So we were slightly better than the other paper because, so we had two good things about our work. One is reduction of background and use of Zenlike Moments, which actually helped us to have a slightly better performance than the other existing techniques. And these are some of the results here. This is from another paper we compared. This is from another paper. They gave us the results, and this is our method. So you can see here, and this is the ground truth. The green one is the ground truth. This is the ground truth, and this is from another paper, and this is our technique. So you can see here, ours is better than the other paper as well. So in case this is the ground truth, ours was able to find out both English text as well as the Chinese text more accurately. You can see here. And this is one of the most toughest one. The text is there. Maybe you can't see it as well. Even the image is not able to see because the text is as the same color as the background. The other method failed, whereas our technique was able to pull it up here. And even this one we are able to pull this as well. Very better, far better than the other existing method as well. And some more results with the data set. You can see here, we were able to detect this as well. Maybe vertical text as well, we are able to find out because our Zenlike Moments is rotationally invariant. So we are able to detect the vertical text. Some horizontal text, which has got say this has got an orientation, some angle. Say for example, this has got about 20-degree angle with respect to the horizontal scale. Even this was able to be found out from the algorithm as well. Okay. We had some failures with our algorithm. For example, the Microsoft, which is one of the most difficult thing, we were unable to do this. This was not clear, and this is impossible thing. Some problem with this. This was again having the background was very poor. We had a same background, and the text was almost having the same the regularity as the background. And in this part, the text was covered by a fence kind of stuff, so we were unable to detect this as well. So these are some of the limitations we had with our method. So I'm just going to finish off with this. What we did is we had a better algorithm which gave us a better score when compared to the existing techniques. Our method worked well for two different things. One is removal of background. Another one is use of this Zenlike Moments. So they were rotationally invariant. All the features were non-redundant, which means they added unique information. And finally, as I told you, this one was also helpful to us the use of variance and entropy was helping us to locate the regions where the text was. And this work was published in this International Journal of Intelligent and Fuzzy Systems. If you want, you can have a look at this particular paper. The code is also given for this. So these are some of my collaborators. We worked across in different countries. We worked across, and we got this paper published. And coming to various other research directions, if you want to work around, this is something very interesting. If people are interested, they can also work on curved text detection and recognition. So you have to find out the curved text, and you need to mark them very accurately. This is something one of the most tough one of the challenges as well. The current challenges on this. So you can have a new data set is also available, and the code is also available on the internet. You can use this and test. So this is the normal text detection algorithm, the normal one, and this is the curved text detection algorithm, where you have to detect the curved text as close as possible. And this is another work we did with respect to 3D text, where our normal algorithms or normal OCR, okay, the normal Google OCR won't function well with 3D images. So we developed another algorithm where we try to remove the depth as well as the shadow. So once you remove the depth and the shadow, it becomes a 2D algorithm, 2D image. And this 2D image was fed to the normal OCRs, and they were able to identify the text. So we can do a 3D text recognition as well. So we have done some work on this as well. So you can refer to this paper of mine if you're interested in this as well. And other things you can work on is multilingual text detection and recognition, OCR, natural learning process. And you also can work on recognition text in various orientations. This is again another one big challenge, you got a big challenge in this. And if you're interested, you can also contact me with this. This is my email ID. You can just contact me and on this email ID. And thank you very much. If you just give me a few more minutes, I'll just explain you my research group here. So we belong to this pattern recognition and machine intelligence group in Chantal University. This is basically my university here. We take in quite a lot of students as interns. So many students from India visited our university, and they worked along with us. So we offer some paid internship for them. So they work with us like 2 to 3 months with us, and we develop quite a lot of work. So some of the works are the medical domain as well. So we have done quite a lot of work on segmentation, ultrasound image segmentation, which is one of the main works we work, and classifying lesions as well. We work on through that. And we have developed our own unit model, which is called we have a unit model, which is called the RAD-UNET model. You can search this name, and we have developed our own unit model for segmentation as well. And these are some of the other works which I've done as well. We are able to do a volumetric analysis of the lesions as well, which are done in the cases. With this, I end my presentation. So I'll just go back, and if you have any questions, you can ask me. Yeah. Okay. Thank you very much. If there's any questions, you can ask me as well.
Thank you, sir, for your presentation. Hello, Sudhir Kumar. Sir, please.
Yes, ma'am.
Sudhir Kumar, you can please ask your doubt.
Should I stop the share?
Yes, you can, sir.
Good evening, sir.
Yeah. Go ahead.
Sir, can I use
Can I use legendary moments in place of Zenlike moments, sir?
Yeah. Yes, of course. Basically, legendary moments are also shape descriptors, right?
Yes, sir.
So you got algebraic moments, you got geometric moments. I think legendary moments come under the geometric moments, and you also have U moments as well.
Yes, sir.
Yeah. So the need why we went in for Zenlike is an orthogonal. So as you know, orthogonal means uniqueness. So as you increase the order of the moments, you get unique features. Hello.
Yes, sir. Yes, sir.
So that's only the reason. I haven't tried on the legendary moments, but I've used U moments in another field as well, and they've given me some good results as well.
Fine, sir. Okay, thank you, sir.
Yeah.
Hello.
Yeah. Go ahead.
Hello, sir. Good evening, sir. This is Nishakar.
Yeah.
Sir, can we use this technique for the brain tumor detection, sir?
Yeah, of course. See, the point is, these moments are shape descriptors.
Okay.
Okay. I have used this Zenlike moments for the following thing. One is face description. For biometrics, I have used, which means different faces have different uniqueness. So I have used it. I have used for retinal blood vessel segmentation. I have used Zenlike moments.
Okay.
If you have a unique shape, then Zenlike moments can be able to describe that shape.
Okay. The shape must be unique, sir.
It doesn't need, yeah, you have to have different shapes, right?
Yes, sir.
Yeah. And if you want to find out a blob or something like that, you can easily find out.
But
So are you
shape
speaking
may
in
not be
terms of
uniqueness, sir.
segmentation or classification? If I ask
Okay.
you.
But the tumor shapes not uniqueness, sir. There are variation.
Are you trying to identify the? No. My question is, are you doing a classification or a segmentation?
Segmentation, sir.
Segmentation you can use. You have to run the Zenlike movements, as a sliding window technique.
Okay.
And if you can run it across on a sliding window technique, and for each and every pixel, you can give it.
Okay.
For each and every pixel, you can give a global score for it. Yeah. And based on the score, you can get this information. Yeah.
Okay.
Yeah.
Thank you, sir.
Yeah. I have a paper on PLOS one. If you want, you can refer that paper. Yeah. Any other questions? Yes, Anand, go ahead.
Hello, sir. Can you hear me?
Yes, Anand, go ahead.
Actually, sir, there are so many deep learning technology for detecting the text and images. So nowadays, the deep learning was a very evolving technology. So, so many algorithms. Can you suggest some of the algorithms which is very accurate to recognize the text features on the net?
Deep learning algorithms. Okay. So basically, you can look into region-based CNNs.
Okay.
Because text is a region, you can work on region-based CNNs. For example, let me write it here. So you can look into things like RCNN, faster RCNN, YOLO. So these basically find out where the text is in the image. Say, for example, this is your scene image. This is your text. So they will be able to find out where this text is. They should be able to do it. But after that, you have to do an additional step where you have to, you have to do a double check on that. Are you following? Sometimes these CNNs can give you a false alarm as well. So to avoid that, what you have to do is you can recognize certain regions as text. Then you can do one more, classification on the top of that particular region. and you can call it as text or non-text on that. That's possible. Yeah, I think you can use. I think many people have used it. RCNN, faster RCNN, YOLO. There are loads of algorithms, deep learning algorithms are there on this. Yeah. Anything else?
Good evening, sir. This is Vikas, and I just want to ask that back propagation is really useful for the shape and size, recognize the shape and sizes.
Back propagation. What do you mean to say in the neural network?
Yes, sir.
But back propagation. Can you repeat your question for me, please?
Actually, I want to ask that back propagation is really useful to recognize the shapes and sizes.
Back propagation has nothing to do with the shapes and sizes. Back propagation is a way by which you generalize or train the neural network.
Okay.
That's a normal algorithm by which the neural network trains.
So segmentation is a part of the back propagation or just a different thing?
No. What is it? What's the question, please? Come again.
Segmentation is the part of the back propagation or different things?
No. Segmentation is different. In computer vision, you have two different things. Either you work on a classification or recognition process, or you work on a segmentation.
Okay.
Back propagation is an algorithm by which you train the neural network.
Okay.
That's a difference. Yeah, go ahead.
Can you tell me deformations in the neural network?
I can't hear you. Your voice is breaking for me, please.
I just to ask that deformation in neural network.
Deformation of the network. I'm sorry.
Yes.
I'm unaware of the term. Sorry, I haven't come across that term. Deformation of the network. Sorry.
Okay.
I'm sorry. I'm breaking. Your voice is breaking a lot.
Okay, thank you, sir.
Hello. Hello.
Hello.
Yes.
Hello, sir. I just want to ask that.
Aditya, can you hear me?
Yes, sir.
Yeah, go ahead.
Yeah, sir. I want to ask that will the Zenlike Moments will work on the irregular text, sir?
Yeah,
irregular text.
obviously. Zenlike, see, for example, what information do you get from a Fourier transform? In Fourier transform, you get the frequency, which means the number of repetitions over a time interval. So the input could be anything. It could be a sinusoidal signal, it could be a square signal, it could be anything. But actually what happens, it gets multiplied by the basis function and it gives you the frequency. Similarly, you take any image, you give it the basis, let this basis function be the Zenlike polynomial. So what you do is you take the basis function, you multiply with any of the images, you get some kind of information, and those information is unique.
Yes.
So it can be used for, say, you can use that like to do anything, say shape, any kind of shape information. If you want to extract, you can use that like to do that.
Sir, but if the image contains the text will be in irregular shape, sir, like in irregular orientation, then the Zenlike Moments will can it recognize that, sir, text?
What do you mean by say for example, let us take this example here. Let us say, yeah. So here, these are two different things here. For example, let us I'll erase this. So in your case, let us say you have been asked to identify this region from this region. When you apply Zenlike Moments, this region will be having some kind of a unique description, whereas the background, let us say this is an irregular thing, correct?
Yes, sir.
So this has got something else. Can you see this? This shows you some other difference. The shape is different, right? So basically, you can use this information to differentiate whether this is a background or this is a foreground and this is a background or something like that.
Okay. Okay.
Am I explaining you clearly or?
Yes, I got the point.
So for Zenlike Moment is basically a shape descriptor.
Okay.
Okay, that's all it is. So for Fourier transform, for example, if you have a sine wave and you give it to a Fourier transform, let us take this for 1 second. So 1, 2, 3, 4, 5. So what you do is you get a frequency of 5 here. This is what it says. So when at 5, it's just a nice peak, which says it has got 5 different ups and downs. Similarly, when you take the input image and give it to a Zenlike moment, it gives you a description of that particular image in the Zenlike transform field. That's all it is. Okay.
Sir, then can it work on the reflection, sir? If the text is reflecting, then can the
can you reflection
means like if the text is on somewhat of mirror, sir, like if it is placed somewhat on the mirror.
A mirror is basically a plane surface, right?
Yes, sir. So if the text is reflecting,
for example, this is a plane surface. This doesn't have any shape. So the Zenlike moment is 0.
Okay.
Can you see it?
Yes, sir. You cannot
have
see
a
the text.
pattern, right? So what is the need to have how can you extract a shape from a plain background?
Right.
Isn't it? If there is a pattern, I mean pattern as a shape, then you should be able to extract the uniqueness of the pattern using Zenlike moments.
Okay, sir.
And each pattern, if you say each pattern is unique, then you should be able to have unique Zenlike moments for each of those patterns.
Right.
Okay. Yeah.
Yes, sir.
Any other questions? Okay, I'll share this. Okay. Fine. Sorry. So, any other questions?
Sir, good evening, sir. This is Prabhakar. My question is regarding the neural network, sir. Sir, you said about the static feeding of network from one end, right? And I want to know different types of neural networks, sir. How we can classify them with their attributes?
I think you got loads of networks like radial basis functions, probabilistic neural network. I think there are loads and loads. I think this particular neural network has been saturated been dealt with for longer time. You don't really need to know much about, you have a black box currently in MATLAB. All you have to do is extract the features, give it to the neural network, and select which particular neural network you want to work on. Yes. And some of the ones like, are probabilistic, which means they give you a score for each of those things. And some give you a value 1 or 0. Other gives you an output as a score. Okay, and using the score, you can do it. And some others gives you something like a radial basis function. Sure. I think there are so many varieties of neural networks. And I really don't, get deeper into that. I just use that neural network, to be honest. So my expertise is more about in terms of, extracting the features. So so if you extract the features, you can use neural networks, you can use SVM, you can use random forest, you can use LDS, so many different, classifiers are there. You can, the best way is to, those are classifiers. And classifiers are going to be a black box. You don't need to do much in that. So as long as you extract the features far better, the classifier is going to give you an output.
Sir, thank you, sir.
Yeah. So my advice for you is the neural networks and the classifier part have been saturated for a long time. So there's no point in re-engineering those at this point of time. So you can just think about extracting the features in a far better way.
Okay. Thank you.
Yeah.
Hello.
Yes, Magesh.
This is Mahesh, sir.
Yes, go ahead.
My doubt is here we using pattern matching, that means text recognition. In this context, we use some string matching algorithms. Is it possible or not, sir?
String matching algorithm. So you mean to say
yes, sir.
You are recognizing the text, right?
Oh, yes, sir. Yes, sir.
Yeah. So I'm not dealing.
Yes.
So there are 3 steps in this process. First is,
okay, sir.
Suppose you take a video the video has got many frames. First
Okay,
thing
sir.
is, out of those frames, which frame has got the text? The first thing is
Okay, sir.
detection of text in the frames. The second thing is called as localization. In that frame, where is the text? It can be in the top right corner, between the middle left corner of the OCR or something else, where you call it as recognition.
Okay, sir.
So my process, I have worked. This is a huge. The end-to-end system is a very huge thing,
Okay.
and many
Okay,
people
sir.
just concentrate one of those. Either they concentrate on detection, localization, and recognition. So I have worked mainly on localization, and that too, you can extract the text regions, pass them to, then you have to divide them into small, or you can pass it as a text. Rather than passing it as a character, you can pass it as a string to the OCR and see how well it is detected. That's the last step.
Okay, sir.
Yeah, but OCRs are there. You can do recognition as well. Yeah, definitely. But that is the last step of the process.
Okay, sir. Thank you, sir.
Yeah. Any other questions?
Thank you so much, sir. Thank you for your presentation, and we are very happy to this 1.5 hours is really is a wonderful session to us. We are connecting with deep learning and how the real-time natural data are extracted from the images, and giving with your valuable ideas. It was very helpful to us, and we are thanking for your session. And of course, we are looking forward for our upcoming events also. Thanks for your cooperation. You want to say anything? You can say, sir. Please give us some word about this and people.
Okay, guys. Thank you very much for your listening. So as I told you, I work on these areas like deep learning, machine learning, and we also have internship opportunities for students. So I take every year at least 4 students from India or from Malaysia. They come and work with me in Chantal. This year we couldn't do it, but we still work on remotely. We do some papers remotely. So if you're interested and you've got some interest towards deep learning, machine learning, and you would like to work remotely with me, feel free to contact me. So on my email ID, and you can just Google my name. You should have seen my ResearchGate score, ResearchGate, or Google Scholar. You should be able to get my email ID, and you should be able to send me an email. Okay. Thank you very much for your patient listening. Okay. And thank you. I just sign off then.
Thank you, sir. Thank you so much.
Okay. Bye-bye.
Priyanka, ma'am, please. Over to Priyanka.
Thank you so much, sir. Thank you so much for your thought-provoking presentation and informative session. Thank you so much, sir. Thank you, sir. Thank you so much, sir. Thank you all the participants who have participated today. And we will meet again in tomorrow's session at 5 o'clock. We will share the link in the WhatsApp group. Thank you, sir. Thank you so much. Thank you all participants. Before that, we will share the results of coding session today.
Ma'am, you can end the session, ma'am.
Yeah, I'm ending the session, ma'am.